In this video, I would like to show how you can use a analog value, as they call it in Technische Alternative, in this TAPPS2 program, to hold up to 10 digital values. Now, analog is actually digital, and these values here are binary. Anyway, you sometimes run out of inputs, outputs on the CAN bus, or if you even want to link it to Home Assistant or something. So in some cases, you can use something like this to have more digital values embedded in one value, in this case from 0 to 1023, which equals 10 bits. So what we have here is to show how you can do that in TAPPS2. First, I can select here for the demonstration purposes, am I going to use the system time to have a number that keeps changing for demonstration purposes, or if I switch that off, I can select the number here manually, as in right now 1023 is all the bits switched on, whereas 0 is everything switched off. So let's just leave it at 1023, but go back to the system seconds counting. So this number just goes from 0 to 59 the whole time. Anyway, with one range function, selecting the binary decoder and putting these values in here, say I want 10 thresholds and starting from 0 up to 9, then I can have one value from 0 to 29 translate into bits as outputs on-off values here, or binary values. And notice I have the simulator running here in TAPPS2, which is up at the top. I can stop it again here. So with this TAPPS2 program, I simply press play, and it's using the system time right now from my computer to input numbers into this function here. Anyway, we can see the bits changing, and I have two more functions here that does the opposite. And of course you wouldn't normally do this, but this is simply to say we can translate this number into 10 bits, and those 10 bits in turn can translate back into a number over here. So what you see, the system time here comes out over here again as the same number, and to see that a bit more clearly, I have the system time here again, so you can see how the seconds coming in through the functions come out here as the same number. Or if I switch it off, which I can also do here remotely, I can enter any random number, 548 or 584 here in this case, comes out at 548. Now I've fixed it to that, and we can go down here and see what are the bit values for these. Now it doesn't say numbers here, but AB is number 1, bit number 1, and greater than J is number 10. So in this case it's bit number 4, 7, and 10. Those bits combined will give us the 584. Now a little bit of trickery here. To make it from decimal to binary is simply using the range function. It only has 10 inputs, so we can only do 10 bits. And likewise, to get it the opposite way, there's only a limitation of 10. Otherwise, the number in TAPPS2 could be much higher, but these functions just don't support it. You could make a mathematical function and strip the first 10 bits and have another 10 bits in the same one value if you want. But for now, I'm just going to show up to 10 digital values. For changing bits back into a value from 0 to 23, so actually a decimal value, we need two functions, or I'm not aware of any function that does it directly. So the range function offers us binary decoder, but there's no binary encoder. It's just not in the list here. So anyway, I'm using the multiplexer function instead. So in the multiplexer, it's actually the analog function in TAPPS2, and then I select, instead of all these minimum, maximum, whatever, I can choose multiplexer and demultiplexer. So with the multiplexer, I can then assign, let me just show I didn't change that. With the multiplexer, I can assign values, and look how I do that a little bit weirdly. I have every even bit be negative, -2, -8, -32, whereas the odd bits are positive, 1, 4, 16, and so on. And the only reason for this is that the output from here, we can turn the timer on again, so the system seconds, you see the value here, -8 and -2, depending on what the value actually is, but they're negative because this function is an old legacy function from the first gen technology from Technische Alternative, like for instance a UVR 1611, and because it's set up to be all the even values here are negative, then you have to make this a negative number, so -32 into here becomes +32, otherwise this result will not compute correctly. So we can't really see anything in here because that just adds it up, but of course in the sum function I choose sum in here and that brings the correct result. So this is how it works. And what can you use all this for? Well, yeah, it is actually useful if you have this limitation, and here we can see it in a kind of manual way. Here I have 10 digital values I can alter individually, and at the moment 1, 2, and 3 is switched on, which gives me a value of 7 in decimals. If I switch on the 10th bit, it jumps up to 519. I can switch these off so we can see a more familiar number. Only the 10th bit gives us 512, and so on. If I choose a 9th bit, 256, and so on. So if I turn on all the first 8 bits, I should get 255. Why not 256? Because 255 is all bits on, while all bits off are 0, of course. So the 256 combinations is 0 to 255, not 1 to 256. Of course, you can add 1 if that's what you want. Anyway, that's as much as demonstrating how this could be done in TAPPS2. And in particular, I need this because I want to integrate UVR devices and the CMI into Home Assistant so they can talk together, with the CMI mainly being the placeholder for the values, like is the light on or off, is this pump running, and all that. But then the Home Assistant will be able to talk to the CMI to send commands, and likewise read back what is actually going on, so we can have Home Assistant integration. Yeah, so that's it for this video. Thank you for listening and watching.